Thank you very much. First of all, I would like to thank you the invitation to be here and to share with you some of the results that we are doing in our laboratory. And of course, the main motivation of part of our work is precisely related to making electronics more sustainable. So this is one of the targets. And today I will talk about transparent electronics. This is just a brief photograph of my campus. The Nova University has 9 faculties, and this is the Faculty of Science and Technology, and over there you can see the Ocean Atlantic on the other side of Lisbon. So we have inside the lab, the laboratory, several scientific areas: transparent electronics, also paper electronics, which is also related to sustainability. We use paper, cellulose, and other renewable materials for electronics, electrochemical devices, some work on biosensors, and also on solar cells. So concerning the short outline, because I have only 15 minutes today, I will talk a little bit about the history of transparent electronics, some of the applications. After that, the actual needs, what we are looking for in terms of technology, and after that, some future perspectives related to this specific technology. So transparent electronics, I used to say that was a dream that became reality. I got my first ERC advanced grant precisely in 2008 on this subject. And in 2004, there was a famous paper published by Professor Idio Ozono at Nature, where it shows that it is possible to grow, to deposit on flexible substrates a new type of semiconductor based on metal oxides. So he's using an amorphous indium, gallium, zinc oxide materials. And one of the main applications for these particular field effect transistors or thin film transistors is for display applications. And these new materials, they are now substituting the conventional amorphous silicon. So we can say that we are now in the presence of a new class of electronic materials. So we can work with copper oxide, with zinc oxide, with indium tin, gallium oxide, and besides that, we can also perform some composites, or we can add more than one metal oxide and explore in a single material different properties. So this is quite appealing, and this is quite interesting for these for metal oxides, which is not the case, for example, if we are using covalent semiconductors like silicon. So just in 2006, we organized at the Materials Research Symposium Society a symposium on the first symposium on transparent electronics. And even only two years after this the booming of metal oxides for display applications, some companies and some universities start to have some integrated devices and some display prototypes. So nevertheless, if you are working with the industry, of course, you need to have stability with your electronic devices. And for example, since metal oxides are used a lot as gas sensors because they are able to promote a lot of different reactions at the surface of the material with the gases that we want to detect. In fact, if we stabilize and if we passivate in using an appropriate material, these devices, and in this case we are using top gate thin film transistors, it is possible to have very stable transistors. And here in this graphic, in the first part on your right, we have the IV characteristic, the electrical characteristic response of a transistor. And even after 10 months, you can see the electrical dependence is exactly the same. So they are stable. And another aspect that we need to take into account, especially if we work with the industry, is reproducibility of the material and of the devices. And here, for example, we have some results that have been obtained within an European project that was finished some years ago. The name was Orama. And here we have the same electrical characteristic of these transistors, but in this case for 168 transistors. So, and as you can see, all the curves are coincident. So the devices are stable and are reproducible. So here one of the first demos using a flexible display using a polymeric substrate. All the active metrics was done here at our laboratories, and the integration with the OLED part was done at TNO laboratories. So, of course, the GIZO, this gallium indium zinc oxide material, is already adopted by the industry. We have already some commercial devices using this type of technology. And of course, the main advantages are the high resolution. We are working with transparent materials. They also present a high mobility, electrical mobility. The mobility is like a figure of merit for these particular transistors. Also, the on-off ratio is higher. They have a low power consumption and also a low noise interference. And this is particularly important, especially if you are working or if with touch screens. So also in 2012, we published a book on transparent oxide electronics, and if you are interested, you can read it. So all the book was done by us, and besides the material itself, N-type, P-type oxides, we have also some chapters related to some devices and to some applications. Also, this ERC grant that I got in 2008 was considered a success story by ERC, especially due to the impact that these type of materials have in electronic devices, not only in terms of cost, also in terms of electrical performance, and also in terms of environment and sustainability. So actually, what are the actual needs? Of course, if we go towards high performance and low cost electronics with sustainable materials, is that possible? Of course it is, and flexible electronics, I guess, in my opinion, is a golden opportunity for oxide thin film transistors. So here it's a little bit the evolution of electronics. So we are now working with the trillions of devices, and of course what we are looking for is for a reduction in cost for all these electronic applications. And also we are now facing the Internet of Things, and everything should be connected. So we need to have electronics, low cost electronics. We need to have a lot of sensors, but at the end, we need to have to produce all these materials and all these technologies in a sustainable way. So the need for sustainable approaches and following also the sustainable development goals, we are looking for the need for low cost technologies and also low temperature processes. And this is what we are doing exactly in our laboratory. So the need for sustainable approaches and following also some demands from the European Commission. Maybe you know that in 2017 was presented this graphic with the list of critical raw materials. And here, as you can see, we have indium and gallium. And of course, in order to avoid the use of these scarce materials, we are now moving from, instead of using indium, gallium, zinc oxide semiconductors, we are substituting gallium and indium by tin and zinc. This is what we are doing also in our laboratory. In terms of technologies, of course, we are working a lot on printing technologies. And here I have an example of a conventional microelectronic process using photolithography. And for example, just to pattern a single line using the conventional process, you need to have 6 steps. And if you are using a printing, you just need to have 1. Of course, we have a tremendous cost reduction in more than 64%. We don't use vacuum systems. We don't use photolithography, photoresist, and also the waste. We are not generating waste by using these printing technologies. Concerning the low temperature processes, so here in these graphics, I present you just an overview about thin film transistors produced by a solution process, not using physical processes like sputtering or physical evaporation. So here what we observed over the years is that the first devices using just a solution process, they need to have a very high final deposition temperature, but over the years we are now able to produce these metal oxide semiconductors using very low processing temperatures. And simultaneously, if we analyze the same devices in terms of mobility, as I mentioned, mobility is like a figure of merit, we observed over the years an increase in terms of the electrical performance. So we are optimizing a lot, all the chemistry associated with these, with the precursors we are using, and also we are not only using temperature, but also we are using other sources of energy, like, for example, radiation. So now briefly some examples then at our laboratory. So here examples using ZTO instead of indium gallium zinc oxide. So it is possible to obtain work with sustainable materials for these particular devices. The same, we are able to use a solution process. So here it's an example of some devices using just a spin-coated precursors based on ZTO. Also here, at the beginning, we start to mimic a little bit what was done by sputtering with gallium indium zinc oxide, and also we succeed to have similar results using a very low cost technology like spin coating. And of course, since we are looking for low temperature processes, instead of using a conventional reaction based on sol gel, we are now using a combustion reaction. So in that way, and if we add, besides the temperature, if we add the UV radiation, we can decrease by by more than 200 degrees the final deposition process. Here an example of a thin film transistor, and the final deposition temperature was just 150 degrees, which is compatible with the use, for example, of plastic substrates or even paper. So again, this is an example presented by Evonik, a company where the display, all the layers we need to produce a display have been done using a printing process. So also here are the other examples, some TFTs deposit on flexible substrates to be used as direct detectors for X-ray dosimeters. So, sorry, other examples of displays. For example, here we have ultra high resolution display with TFTs done in our laboratory. So since we are using and we are applying these metal oxides as semiconductors, we can use at different integrated circuits. So here some examples of other circuits like inverters, NANDs, some logic gates, current mirrors, and so on. And also some examples, also the possibility to incorporate these devices on textiles. So also here some results of an European project that was coordinated by Cambridge University. So in terms of future perspectives, so we are also working on perovskites, not only for solar cells, but for thin film transistors. As you know, metal oxides are very good N-type semiconductors, but for some applications like CMOS, we need to have P-type semiconductors. And these perovskites, they have an excellent behavior as P-type transistors. So here an example of some transistors produced at a final deposition temperature of 150 degrees. And also one of the advantages of the process we are using in our laboratory is that yes.
Just another minute, thank you, that'd be great.
Okay, I'm just finishing, thank you. So okay. These have been produced without using glove boxes. So on flexible and also some other perspectives. We are able to produce graphene out of a polymer just by using a CO2 laser out of paper. And this is just the final remarks. And I just would like to thank our team, and also I would like to thank the projects that are financing this type of work. And also I would like to thank you for your kind of attention. Thank you.